International relations. That's a big topic. And in the introductory video, I mentioned to you that strategic international relations is both a big idea and a little idea, in the sense that there's both some substance going on and some method going on. And at your stage of this journey, that might not be obvious to you, but hopefully as we go, you'll begin to see that strategic IR is both big and little. Before we even add strategic to it, international relations is big. There are hundreds of countries and billions of people. There are millions of firms. And it's our job, whether we're strategic international relations people or any other kind of international relations person, and whether we're mathematical international relations people or any other kind of international relations person, no matter what our ideological bent and no matter what our methodological bent, we have to make sense of a world that is so complicated that it almost seems hopeless to try. But it isn't hopeless to try. The question is almost the same problem that a cinematographer faces when they're making a movie. Not that that's on my mind right now. You know, you need one kind of lens to zoom in. If you want to get a close-up of somebody and observe all the details of their beard and all the bad pores that they have after a long day and just how many follicles have died. If you wanted to get a close-up of that, you would use one lens. And if you wanted to get a pan shot to get a sense of the entire spectrum, you know, if you wanted to zoom out and just get some vantage, some vista, then you'd use a wide lens. You'd use a different lens. But either way, you'd use a lens, right? You would use some curved piece of glass to try to capture whatever you wanted to about what you were trying to observe with the camera. And so just the same way that sometimes we'll zoom out and look at the entire globe, and sometimes we'll zoom in and look at two countries. No matter what we're doing, we're always going to have a particular level of abstraction in mind. We will have to sacrifice a lot of details whenever we want to zoom out and look at the entire international arena. And we will have to forego a lot of generality when we zoom in and look at any particular process in a narrow way. And that's what today's lecture is going to focus on. How do we take this big world that we live in, this embarrassingly complicated world, how do we put it into a format that removes all the complicating context? How do we put it into a form that strips away unnecessary details so that we, flawed, limited humans with our flawed, limited understanding of things, can hope to make some sense of it? How do we strip away all that? How do we make the problem abstract? And so it turns out that there's going to be three main tools that we use again and again and again, and they're all related. For starters, we need to try to find a way to establish clear patterns of reasoning that are reliable. So how do we come up with arguments, logically valid chains of conclusions that allow us to step by step start from some assumptions or some axioms and arrive at some conclusion that we didn't know before? How do we reliably generate knowledge that way? We're just going to try to remove all the ambiguity. And in order to remove all the ambiguity, we remove all the context. We remove all the indexicality. We'll talk about that here in a little bit. After we've talked a little bit about introductory logic and statements and operators on statements, then we'll talk about sets, which are a very, sort of the most natural mathematical tool for us to collect all of the objects in a given class of objects. So for example, if I want to talk about every country in the world, maybe every country that recognized by the United Nations or something, well then I want to talk about the set of all countries at that point in time. Well, what's a set? What does it mean for me to do that? How would I write down in a reliable way that I am talking about some object that is all countries, and I mean one thing by that, but then within that one thing, that set of all countries, we also know every element of it, every country, the United States, China, Canada, Japan. How do we organize ourselves that way? And actually, really, the verb that I want to use is organize, because sets and logic are a wonderful way for us to keep our thoughts organized, which we're going to have to do if we're going to survive trying to figure out all of the complications of international relations. And then finally, we'll talk about functions. And functions, you've probably seen functions before, maybe not the way that we're going to talk about them. What a function is a way for us to encode a rule, a way of saying, take one set of objects and convert it to another set of objects. So for example, if we were talking about votes on the United Nations floor, then we might start from the set of all countries that have voting privileges in the United Nations. So that's one set. All the countries, United States, Nigeria, Spain, right? Azerbaijan, they're all in there. I have a set of all countries. And on a given vote, maybe they vote yay, nay, or they abstain. And so there's actually a little set there of all the possible votes that they could levy. Well, how do I take this one blob, this blob of countries, and relate it to the blob of votes? And you're like, for this I pay. Actually, it's pretty interesting if you let yourself just think in terms of the blobs and the dots and the arrows, I swear. So how do we link these things together? Well, we do that through a mathematical device called a function. So you'll be talking about functions the same way that you've talked about them before, but you'll also be talking about them in a broader sense too. So my goal for today is to talk a little bit about logic, a little bit about sets, and a little bit about functions. And it's not that today is going to be deeply substantive or anything. On the contrary, to be honest with you. I just want to make sure that we all have the same sort of foundation as we begin to try to build elegant, interesting sentences about the international world that we also think have some chance of being true. So that's our goal for the day. We need to encode the world. Let's get started. So I want to start with logic, a little bit of just basic logic. What is logic? If you view it as a branch of mathematics, it's sort of like the study of patterns of reasoning. And if you view it as a branch of philosophy, it's still the study of patterns of reasoning. It's basically how to make a good argument. So what we're trying to do here is we want to start from premises that we think are true and use those premises in conjunction with one another and the tools of logic to try to arrive at conclusions that we didn't know were true, but that are true so long as our premises were true. And that's sort of the way that we proceed when we're trying to compile knowledge. But in order for us to do any of that, we need to stop and say, what is the atom? What is the building block of an argument? It's kind of strange when you think about the question that way. Everybody wants to talk about what an argument is, and Lord knows we see people arguing all the time, don't we? But what is the atom of an argument? And the answer is, it's a statement. So the building block of everything we're going to be doing in this class, and it's going to be so foundational for our purposes that we're not going to talk too much about it. I just want to make sure that we're all on the same page and acknowledging that it's what's happening. Everything we do is going to be looking for true statements. What does that mean? Well, a statement is an utterance or a claim, and I'm begging the question like crazy right now, because if you say, what's a statement, and then I say, it's an utterance, then you should be saying, what's an utterance, fat bald man? We're just going to have to agree to allow this definition to be a little bit murky. This is what you might call a naive version of a statement. So a statement is a claim or an utterance or some piece of linguistic content that is unambiguously true or false. What do I mean unambiguously? Well, it means that it's always true or always false, irrespective of the context. So for example, let me give you an example of a statement. And it's the one that I mentioned in the introductory video. So let's say that the statement is, the United States is a democracy. Is it a statement, right? So a statement is a claim that is either true or false or not both. Well, any country being a democracy is either true or false, but not both, right? It can't be the case that you're a democracy and you're not a democracy. So the big question here is, does judgment matter too much in this statement? Well, suppose that we came up with a formal definition of what made a country a democracy, right? So there have to be free and fair elections, or there has to be executive recruitment, or something along these lines. And in fact, there's data on this, right? So every year the Polity 4 project releases a data set called the Polity scores, and that's a number that gets assigned to every country that's between -10 and 10. And the idea is that a -10 is an all-the-way autocracy, and a 10 is an all-the-way democracy. And we usually view autocracies as countries with polity scores of -7, -8, -9, or -10, and democracies as countries that are 7, 8, 9, or 10. So if you have a really high polity score, we call you a democracy. If you have a really low polity score, we call you an autocracy. In the middle, you might call it a mixed regime, or sometimes you see the word anocracy used. Anyway, so we could use the polity scores, which are sort of quick and dirty, off-the-shelf measure to say whether or not a country is democracy. And so now we've removed all ambiguity. So if I say the United States is a democracy, where a democracy is a country with a polity score of 7 or greater, now there is no ambiguity, there is no judgment. The word democracy has been precisely defined. And so our statement is either true or false, but not both, and it doesn't matter who's the one doing the evaluating. So a statement oftentimes relies on clean definitions. So there's this interesting interplay, once we're talking about things that are complicated, between definitions and statements, so that we can try to link plain language back in. We want to be able to speak in plain language. It's so annoying if every time you say, well, whenever I say democracy, I mean a country with a polity score of 7 or greater. That's annoying to say every time. I'm getting tired of myself talking even just now, and we just got started. But that's what we're looking for. We're trying to be that precise. We want to make sure that the indexicality of language, this reliance on context that makes it so efficient, doesn't drag us down. So an example of where plain language helps us a lot. Suppose that I said to you, I feel good today. Okay. So that's a sentence. You probably hear a sentence like that all the time. Nobody in my family ever says I feel good today, so it seems very foreign. Many people say I feel good today all the time, right? These are the people that are in the advertisements for meditation apps. So if I said to you right now, I feel good today, let's just look at the words I, and you're like, this is very strange, but just bear with me. I feel good today. Let me try it without a voice crack. I feel good today. That word I, what does that mean? Well, it's a pronoun, right? It stands in for whoever happens to be doing the speaking. So in the sentence, I feel good today that you just heard, I referred to Rob Carroll, assistant professor of political science at the University of Illinois at Urbana-Champaign, right? Now, if you said that same sentence, I feel good today, you would mean you, a student at the University of Illinois at Urbana-Champaign. The same word, the same sound, the same one letter means two different things depending on who said it. And indeed, if you think about it, if we equip everybody with enough English to be able to say the sentence, I feel good today, the word I means a different thing for billions and billions of different people. Yet, nobody ever questions and says, what do you mean by I? Nobody ever, like, I could say to you, what do you mean democracy? And you'd be like, well, let's talk about it. That's a nuanced and difficult question, right? But I would never say to you, if you said I feel tired today, I'd never say, what do you mean I? We want to avoid relying on things that are so baked into how we use plain language that it doesn't even make sense to question them. We want to question everything. So we don't want to rely on that efficiency that we get. And so the downside is, speaking precisely, speaking in well-formed, unambiguous mathematical statements, like the United States has a democracy score of 7 or greater, it's less efficient, it's more precise. That's a trade-off that we're going to have to navigate in this class. Our brains naturally gravitate toward context for understandable reasons. It helps us to navigate all sorts of different things. And context is oftentimes massively important, right? But our reliance on context is oftentimes the reason that when we're new to programming, for example, we'll say to ourselves things like, man, the computer is stupid. The computer that I'm trying to program is stupid. It didn't know what I wanted. And the thing is, the computer is only going to know exactly what it's been told. And you can think about our goal here as trying to be precise enough in encoding the world that we could tell a computer what we meant by the world, and it would know what that meant, right? It wouldn't have any confusion. It wouldn't return an error and say, sorry, I don't understand any of this context. We're going to supply it with all the context that it could need in order to represent the world. You know, some of the most basic statements are things that you see arise in mathematics. So actually, if I said to you x is greater than or equal to 3, that's a statement, right? Whether it's true or false depends on what x is. So for example, if x equals 4, 4 happens to be greater than or equal to 3, so that statement is true. And if x is 2, well, 2 happens to be not greater than or equal to 3, so that statement evaluates to false. So x is greater than 3 is a statement, and in fact it's like an entire infinite continuum of statements, right? Where for any x that you gave it, you'd know whether it evaluated true or false. It's a property of the numbers that you can't simultaneously be greater than or equal to something and less than it, right? So it either evaluates the true or false. There's no confusion when we think about the real numbers like that. Now think about some of the standard sentences that you might hear said in international relations. So suppose, for example, that we wanted to say country X is more powerful than country Y. What does power mean in that context, right? We need precise definitions to know whether that evaluates to true or false, irrespective of context. There might be some pairs of countries where in one situation, country X is indeed more powerful than country Y. But in another situation, country Y is more powerful than country X. So for example, one country might have an awful lot of hard power. They have a lot of guns and bombs, right? They've invested in their military, and so they have a lot of traditional hard power. The United States is more powerful than the Vatican City in the sense that the United States has nuclear weapons, and the Vatican City has Swiss men that hold pikes. But in other contexts, more powerful than might mean different things, right? So if we're talking about purely soft power, then a country that seems very strong, like North Korea is very strong, right? They have nuclear weapons at their disposal. But in terms of soft power, they don't have as much of that. So if we were talking in terms of soft power, Vatican City is more powerful than North Korea. So the precise definitions are going to be conceptually very difficult, because what constitutes as more powerful can mean a lot of different things in a lot of different contexts. And so anytime that I'm talking about a statement and I need it to be unambiguously true or false, and you don't quite know what's going on, not that this is going to happen or anything, check the definitions. Ask me, hey, what do you mean by more powerful than? What do you mean by? And oftentimes there won't be a convincing answer because there's insufficient conceptual work done on a topic, or the answer might be only in the context of a given model, right? So if I say that one country is more powerful than another country in a bargaining model, then I might just mean that their probability of victory is higher if the countries fought a war, something like that. But throughout, if you're confused, it's good to know what you're confused about. And sometimes it'll be something technical, and sometimes it'll be something conceptual, and those things aren't the same. Check the definitions often, because one thing that international relations needs more of, to be completely honest with you, is precise definitions of what we mean by all these concepts that we use. And what I aim to do in this class with you is show you some of the better defined terms. We could talk about statements all day, right? So whether a country is a democracy or not, whether two countries are at war or not, whether an alliance is maintained or not, whether a sanction is effective or not. There's all sorts of different statements that are out there, but it's not very interesting just to think about statements in isolation, right? I mean, so if I just walked around uttering statements, even if they were all true, if they weren't especially well linked with one another, you'd be saying to yourself, what is this guy talking about? You're probably already saying, what is this guy talking about? But you know, some people, they can just keep saying true things, but it isn't always linked or relevant. One interesting question is, hey, if I have a couple of statements, if I have multiple statements, can I combine them to form new statements? That would be sort of the first step toward trying to link statements, would be taking two statements and making a new statement out of them. So let's talk about how to do that. And to do that, we're going to talk actually about 7 operators that come up pretty often. And it's going to be a little bit intimidating, and we're going to have to talk about them in 2 parts, because 2 of them make a lot more sense after we've talked about sets, and I'm really sorry about that. But basically what we're trying to do is figure out ways to make new sentences out of old sentences, where statements are kind of like sentences, and you know how to do that, right? You know how to make 2 sentences into a third sentence, and it turns out there's going to be some deep relationships between the linguistic tools that we use to link statements together and the mathematical tools that we use to link statements together. But in order for any of this to make any sense, we're probably going to have to go to the whiteboard. So follow me. First, zoom, and then zoom, and then zoom, and we're at the whiteboard. So the device that we're going to talk about to introduce some of these operators, it's called a truth table. And truth tables, you can use a truth table actually to make an entire theoretical argument if you were so inclined, so long as it was a relatively simple and straightforward kind of argument. Truth tables are great not just to make arguments with, though. They're also, if you ask me, the easiest way to see what's going on with some of these mathematical machines that we use to develop logical statements. What I do when I make a truth table is I list all of the possible combinations of truth and falsehood of the statements that I'm trying to combine. So just to give you one example, if I've got two statements, P and Q, where P is, let's say, the US is a democracy, and Q is Canada is a democracy. So suppose that I've got two statements, the US is a democracy and Canada is a democracy, where in both cases a country is labeled a democracy if their polity score is 7 or greater, which in this case, in the world that we live in right now, that's true for both of them. Great. So now I've got two statements, P and Q. There are 4 possible combinations of truth and falsehood of those statements, right? So let me write out these with columns. So there's going to be 4 rows in this 2-column data set that I've got so far. So for P might be false or true or true. And Q might be false or true or false or true. So you'll notice now, in these 4 rows that we have, we've got all 4 possible combinations of the constituent statements P and Q. I'm going to try to combine P and Q to make other statements. And you're like, what's a statement? A statement is something that's either true or false, but not both. A statement is something that you can put into a data set like this without it becoming confusing. Now, each row in this data set, of which there are 4, these are all called cases. And so I might label these cases 1, 2, 3, 4, where case 1 is the one where P is false and Q is false. Case 4 is the one where they're both true, and so on. Okay, so now we've set up our truth table. The first step in setting up a truth table is always just listing all of the possible true-false combinations of the constituent statements. You can imagine why this gets complicated pretty quickly then, because for however how many statements I'm trying to combine, I will have 2 to the that many. So if there's n statements I want to combine, I'll have 2 to the n rows in my truth table. So three statements, P, Q, and R, that would require 8 rows. P, Q, R, S would require 16, 32, 64, 128, and so on. I have trouble keeping track of whether Chewy had dinner or not. Oh, we haven't talked about... I have a dog, his name is Chewy. You're going to meet a lot of Chewy in this class, mostly because he's what's on my mind most of the time. I'll cut to some Chewy footage as we speak. Oh, he's a good boy. You probably also noticed the painting of him. So Chewy's going to come up pretty often. So I have trouble keeping track of whether Chewy had dinner, much less 128 rows in a truth table. So, we're not going to use this for very complicated arguments, but for P and Q and R, we can keep track of that. All right? So we've got these 4 cases, and I'm going to link these constituent statements. The United States is a democracy and Canada is a democracy. I'm going to link those 2 statements together to make a new statement, which is something that's true or false, but not both. So the symbol I'm going to use is this this wedge symbol. What does that mean? Well, you can read that as the word and. So if I write P wedge Q, P and Q, that means the United States is a democracy and Canada is a democracy. And is, of course, one of the conjunctions that we use in everyday language to link independent clauses to form compound sentences. Well, what is this but a compound sentence? If I said to you, the United States and Canada are both democracies, when would you give me an F? When would you tell me that I was wrong? Well, you would tell me I was wrong if it weren't the case that P was true and Q was true. We need them both to be true, right? So let's go through this case by case. So in case 1, they're both false. We needed them both to be true, so you give me an F. In case 2, we have P is false and Q is true. We needed them both to be true for the AND operator, so that's still a false. You gave me an F. In case 3, P is true and Q is false, we needed them both to be true. You give me an F. And finally, in case 4, they're both true, and so you give me a true. All right? So whenever we're evaluating these things, try to keep your intuitions a little bit at bay. So the AND operator is precisely defined this way. This is the definition of the AND operator. It is something that returns true if and only if both of the constituent statements are true. So now you might be saying to yourself, okay, I can think of other words that oftentimes link statements, and do they have mathematical analogies? If the word you had in mind was or, then yes. So if I write P VQ, that's just an upside down wedge, right? P VQ, P wedge Q, P or Q. This is P or Q. When I write that, that means that either P is true or Q is true. Now we have a bit of ambiguity that we're going to have to define ourselves out of. Sometimes when you say or, you mean but not both. And sometimes when you say or, you mean or both. But in math, most of the time, we mean or both. We mean or in an inclusive way. So I'm going to define the or operator as follows. In case 1, where both P and Q are false, give me an F. Okay? In case 2, when 1 is true, give me a T. In case 3, where again 1 is true, give me a T. And in case 4, where they're both true, this is the inclusive or part, give me a T. Okay? You could imagine an exclusive or operator, it exists, that would go false, true, true, false, but here we mean we're both. So look at this. When you think about it, I don't want you to get too worked up about a couple of scribbles, but think about it. We took two statements that are either true or false, and that are unambiguously true or false. These are verifiable, clean, well-defined statements. And we've used them to define two new statements. So you gave me P and you gave me Q, and now I've come up with P and Q and P or Q. And not only do I have those statements, I know everything there is to know about those statements' truth values, so long as I know the underlying truth values of the constituent statements. So if I know about P and Q, then I know about P and Q, and I know about P or Q. It's amazing that we're able to take two sentences and combine them this way, and get reliable knowledge on the new statement end based on what we know about the old statement end. There's another way to make a new statement out of an old statement. Actually, this one doesn't even require two. So one thing that happens pretty often is we want to negate a given statement. So I'm going to use this symbol to mean not P. So not P, opposite of P, okay? Where if P is false, give me a true, and if P is true, give me a false. So just going top to bottom here, we go true, true, false, false. Pretty easy. And then just for funsies, let's do not Q as well. Well, in case 1, Q is false, so give me a true. In case 2, Q is true, so give me a false. In case 3, Q is false, so give me a true. And in case 4, Q is true, so give me a false. So these not operators are at our disposal too. So and, or, and not. Those are the three most basic operators. And if you have a statement about anything, you can use the not operator to make a new statement. And if you have two statements about anything, you can use the and or the or operators, right, to make new compound statements. Now, it's really cool that we're able to make new statements out of old statements that way. But again, if all we did was take a big bag of statements and then combine them with ands and ors and nots, it's true, we would have a bigger bag of statements then, but we still wouldn't have generated any new knowledge, right? So generating new knowledge in a world like the one we're in is something to the effect of, if you knew that one statement was true, you would know that another statement was true, right? So in other words, it would be cool if you could say something to the effect of, if a country is a democracy, then it is economically developed. Or if an alliance is between two democracies, then it will be honored. Or if a civil war erupts in a country with low per capita GDP, then it will be a long civil war. Something like that. Something where you begin with the premise, something where you say, if this were true, then I would also know that something else was true. When do you get to take one thing that you know is true and use it to correctly and reliably infer that something else is true? Right? That's what we're gunning for here. We want to take our premises and turn them into conclusions. So how do we do that? Well, the most basic fundamental building block for making an argument of that form is a material conditional, which is just a fancy way of saying if then, okay? So this is just another new statement. It's another operator that combines two statements, and just like and or, it has a particular pattern in the truth table. It's just that this one seems like it has higher stakes, okay? So I'm gonna write P double arrow Q, all right? And you can read that as if P, then Q. I'm going to try to avoid the use of the word implication there, because that's kind of loaded philosophically. But I might say P implies Q there as well, okay? I'm going to start with cases 3 and 4, and then I'm going to double back to cases 1 and 2, all right? So think about if I said to you the following: if you study hard in this class, then you will get a good grade. All right, that's a statement. That's either true or false. If you work hard in this class, then you will get a good grade. When would you give me an F? When would you be mad at me? When would you say, nope, you were wrong? Well, you'd be wrong in case, you would be mad at me in case 3. You'd be mad at me if you worked hard, if P were true, but you didn't get a good grade in the class, if Q were true. So the implication, this material conditional, P, if P then Q, is false in case 3. Okay? So that's exactly the problem with an implication sort of argument like that. That's when you get angry. You get angry when the premise, P, is true, but the consequent, Q, is false. Now, in case 4, P is true and Q is true, so we're happy. That's a T. That's great. That leaves cases 1 and 2. And there's a reason that I tried to introduce if P then Q as sort of like a promise. So the question is, if P then Q, if we view it as a promise, and then either case 1 or case 2 happens, would we feel like whoever made that promise broke their promise? No. Right? So if I promised you, if you work hard in this class, then you'll get a good grade, and then you didn't work hard in this class, would you be able to be angry at me? Well, if ISIS forms are any indication, then yes. However, you wouldn't be angry at me just because of you felt that I broke that promise. Okay? So in other words, we're going to put a T there. So if the premise is false, if P is false in the statement if P then Q, then if P then Q is true. Okay? Now look, those T's in cases 1 and 2 are exactly the same as the T in case 4, right? When I said what's a statement, I didn't say, well, it's something that's true or false, and some of the truths are satisfying and other of the truths are not satisfying. I didn't say that. However, something there is that's a little bit annoying about these T's, right? You'll come to become comfortable with them over time. The word that we use for this sort of part of a truth table is, we're going to say in cases 1 and 2, then the claim if P then Q is vacuously true. Okay? Vacuously true. So it's true, but we didn't really learn anything because we never really tested the claim. We never put the promise under this, we never actually had to live out that promise. It's just a hypothetical to us. Just for fun, I'm going to try not to spit all over myself as I keep the energy levels high! Just for fun, let's look through if Q, then P. Okay? Well, in case 1, Q is false, so vacuously, the statement is true. Okay? In case 2, Q is true and P is false. We would be angry, so that's an F. In case 3, Q is false, we don't have to do any more. The statement is vacuously true. And in case 4, both Q and P are true, so we get a true. All right? So in this example, if Q then P, if you did well in this class, then you must have worked hard, right? That would be something of that form. And what would prove that wrong? Well, what would prove that wrong was a student that did well in the class, Q is true, but that didn't work hard. One of you jerks is just going to be so darn smart that you don't need to come to class. Whatever, it's fine. I always admire students like that, even though I wish that they would come to class so I could learn something from them, but that's a different story. So we have if P then Q, if Q then P. That's our fourth new way of making a statement out of old statements. So we have and, or, not, if then. So our fifth is actually just going to be a combination of these two examples that we just did. So I'm going to come up with a biconditional. It's going to be an arrow in both directions. P, if and only if Q. That symbol reads P, if and only if. And if you look at it, it looks like the implication arrow in either direction, right? Well, that's exactly what it is. So we say that P, if and only if Q, or P is equivalent to Q. P is equivalent to Q when P implies Q and Q implies P. I'm just going to, again, use the truth table to show you the definition of if and only if. And to do that, I'm actually just going to use the and operator on the two columns that we just made for material conditional, right? So in case 1, if P then Q is true, if Q then P is true. So P, if and only if Q is true. In case 2, if P then Q is true, but if Q then P is false. And so we needed them both for the and operator, so that's an F. Give me an F. In case 3, if P then Q is false, and if Q then P is true, well, we needed them both to be true. So that's a false. And in case 4, if P then Q is true, if Q then P is true, our and gives us a true. So let's look at when P, if and only if Q is true. Well, it's true exactly when P and Q are equal to one another, right? I said equivalent for a reason. So P, if and only if Q, is actually just our mathematical crystallization, our logical crystallization of equality of two statements. So two statements are equal, they are truly equal if each implies the other. Well, let me introduce a new term. So in material conditionals like this, if P then Q. In the statement if P then Q, if you study hard in this class, then you will get a good grade. The first part, the P, the premise, is called a sufficient condition for Q, right? So if in the statement, if you work hard in this class, you will get a good grade, P is a sufficient condition. Studying hard is a sufficient condition for getting a good grade in this class. And in a statement of this form, Q is a necessary condition for P. So in the statement, if you work hard in this class, then you will get a good grade. Getting a good grade is a necessary condition for working hard. So these if-then statements they influence your plain language, right? They influence your plain language because necessary and sufficient conditions are things that we talk about all the time. This is precisely what we mean by that. Whenever I say that something is sufficient for something else, I mean that if it's true, then the other thing is true as well. So if I tell you that development is sufficient for democratization, right, then I mean if a country is sufficiently highly developed, then they will democratize. And if I mean to say that development and democratization are the same thing, then I need that implication to work in both directions, so that each is a necessary and sufficient condition for the other. Okay, so we've now introduced 5 of our 7 ways of making new statements out of old statements. And, or, not, if then, if and only if. So if you need to, go back and reflect on those 5. We're going to introduce 2 more, but it's going to be a lot easier for me to do that once I've introduced sets. So let's talk about sets. So sets are one of those things that, again, are so foundational that you don't even notice that you use them. So whenever I say all countries, I implicitly mean the set of all countries. Whenever we use certain numbers, we implicitly mean from a set of numbers. Again, it's hard to describe it without introducing the tools because of how foundational it is. So let me not beat around the bush anymore. So, in a naive sense, a set is just a well-defined collection of objects, and we call the objects that live in the set its elements. Now, again, a question has been begged, because I defined a set as a collection, and then you should be saying to yourself, well, what the heck is a collection? And again, this is why we're going to leave it. You can take advanced classes to try to make all this axiomatic if you want to, and I think that's a great exercise, but for the purposes of this class, let's just be a little bit intuitive with this. Okay, so as an easy example, even though I don't know any of you just yet, I can think about the set of all students in this class. You can think about the set of all professors that you have for your other classes. You can think about the set of all friends that you have. You can think about individuals as parts of a set. But then it comes time to actually write a set down, and that becomes a little bit tricky. So let's talk about how to write a set down, and there's actually two main ways to do it. The first way to write down a set, and again, writing down sounds like a trivial exercise, but whenever I say write down, I don't just mean write down. I mean specify in a way that you could tell a computer how to do it. So write down actually becomes a really important stand-in for properly encode. So how do we write down a set, which means how do we encode what a set is and what its elements are? Well, if it's a little set, then it's very easy just to write out a set in what's called roster notation, where you just literally write out all the elements in a set. So for example, if I have a deck of playing cards, let me get a deck of playing cards. Okay, so I've got a deck of playing cards. So chances are good that you know that a standard deck of playing cards that we use for many games has 4 suits. Every card has a marker on it, and there are 4 of them. There's spades, clubs, hearts, diamonds. I don't know why. Look, this one has the nice property that I can, right? Not a problem. So I can write out the set of all suits, right? I can write out the set of all suits, and it's just, maybe I'll call that S for suits. S equals, and then I just write them out, and these squiggly braces mean treat this like a set. Diamonds, hearts, clubs. See, I'm so glad I don't have to draw this now, because I have no idea how you actually draw clubs without it looking like a really bad set of grapes. And certainly spades are really hard to draw. Boom. I just named a set. And in order to, I specified that this set S had these 4 elements in it. Diamonds, hearts, clubs, and spades. So this is, I just defined it. I defined S. And so each one of these 4 items in S is an element of S. And if I want to express that with a statement, right, I can make statements that use S. I would write hearts, for example, is an element of S, where this little E-looking symbol means is an element of. So hearts is an element of S. That's a true statement. That's a statement that is unambiguously true or false, right? And not both. So that evaluates to true because of how we defined S. What's something that isn't in S? Well, let's think about a Maltese cross. I love the Maltese cross. Isn't it beautiful? It's so pretty. Underrated. Nevertheless, it's not a suit in a standard deck of playing cards. So it is not true that Maltese cross is an element of S. And so if I wanted to write that as a true statement, I would put a slash through that element, and that reads, Maltese cross is not an element of S. I also could have just negated. I could have used the negation symbol. It is not the case that Maltese cross is in S. Easy. So, oh, you're already starting to see. So if we're going to be able to think about international relations in terms of sets, and we're going to be able to use statements of inclusion with sets, like hearts is an element of S, then we're going to be able to come up with statements about international processes once we've come up with the right sets, right? And actually that intuition, if we build on that sufficiently, that's a lot of what we're trying to do here. So you might think about the set of all countries in the world, the set of all firms in the world. You know, you can just introduce these linguistically if you need to. And then if somebody says, well, what do you mean by that? Maybe you write down a little bit more formally what you mean by that. But just the conceptual act of saying, gather all of the certain somethings of a class of things, gather all the countries, gather all the firms, gather all the actions available, right? Gather all the possible bargaining solutions, right? Gather all of these really complicated things into one set, and so that we can call that many one. And actually, one of the inventors of set theory, Georg Cantor, his definition of a set was a little bit too naive, but it also was really powerful, and it was just, imagine a one out of many. It's just the ability to talk about many things as if they're one thing, oftentimes linked through some conceptual apparatus, like everything in the set is a country, or everything in the set is a democracy, or everything in the set is a commodity. We can even introduce sets that are infinite this way, right? So let's just think about the counting numbers, 1, 2, 3, 4, 5. These are sometimes called the natural numbers, and they have a special symbol. They get this special blackboard N, it's called. Right, so this symbol means the natural numbers, the counting numbers. We're going to use these pretty often. And so that set, if I want to introduce it, I'm going to use a brace just to say, hey, this is a set that I'm talking about. 1, 2, 3. I'm not going to be able to write them all down. And I know you'd like me to try, because I would die in the process and you wouldn't have had to listen to me too much longer, and it would be, no, that's a little bit dark. I'm not going to be able to write them all down because there's an infinite number of counting numbers, right? So if you gave me any counting number, if you gave me a Google, which is a 1 with 100 zeros after it, that's more than the number of particles in the known universe. Oh. Isn't it crazy that we can think about that number even though we could never hope to understand it? I'm not going to be able to write these all down because if you gave me a Google, I would just say, and a Google plus 1 is a bigger number. I can come up, you give me one, I can come up with another. So I'm just going to put these ... here, this ellipsis. And that means, and so on, continue. Okay? So these are the natural numbers, or the counting numbers. Just to introduce some other sets of numbers that have fancy symbols like this, you know about the natural numbers, you might know about the integers, right? We call that Z. So the integers are Z, and so that's all the natural numbers plus 0 plus all the negative natural numbers, right? So for that we might go ... -3, -2, -1, 0, 1, 2, 3, ... In order for me to talk about some other sets, then I'm going to need to introduce set builder notation. So let's talk about that. So set builder notation is the more conceptual way to define all the elements of a set. So it gets very annoying to write out all the elements of a set, even if it's a finite set. I don't want to have to write out all 50 states if I want to write out all 50 states. I don't want to write out every country in the world. I don't want to write out every president of the United States there's ever been. I don't want to write out every political party in Italy. How do we define a set in terms of a property like that? So then we go away from roster notation, and instead, we talk about set builder notation, which is, it's a really powerful device. Just the act of writing something down this way is really powerful. I might want to write down the rational numbers, which is the set of all numbers that can be written as a ratio of two integers, right? So I've introduced the natural numbers and the integers, but I want to introduce the rational numbers. The rational number, like a third, that's a really important number. And right now, our two sets of numbers don't include a third. Well, I want a third. A third is really important. So how would I write that? Well, the name of that set is Q. And the set is now going to be in two parts. Okay? So, and I'm going to separate these two parts with this pipe. and that pipe is read such that. Sometimes you see a colon there instead. A pipe or a colon, either way is fine. And that means such that. On the right side of the such that, you're going to get whatever the property is that has to be satisfied, right? So we know that something, x, we'll call it x, has to be written as p over q, where p and q are integers. So on the right-hand side, right now I have the set of all blanks such that blank is equal to p over q, where p and q are both elements of z, the set of integers. And presumably that means that q isn't equal to 0 because dividing by 0 is frowned upon in most circles. Well, all I need to do then is identify what I'm talking about. So on the left-hand side, I'm going to say the set of all x's, all these little x's, such that x is equal to p over q. In general, it's useful for us to use the left-hand side of set builder notation. This, on the left-hand side of the pipe, it's convenient for us to talk about what an x is in this case. Oftentimes, there'll be some implicit universe of discourse. So I'll write the set of all little x's that live in big X, such that little x equals p over q. Okay? Where presumably x is the set of numbers that we care about in this example. Let me give you another example to help simplify things. So suppose that capital N is the set of all countries. And suppose that I define the set D, and by that I mean democracies. Well, D is going to be the set of all x in N, so that implicitly means the set of all x in the set of all countries N. So the set D is the set of all x's, countries in N, such that x is a democracy. Right, so I've used this property on the right-hand side to say, just give me the set of all, you gave me N, the set of all countries, and I want to talk about D, which is a part of N, and it's the countries that are democracies. So set builder notation is really convenient because it allows us to be conceptual when we define things. However, it makes obvious the fact that we need a universe of discourse. We need to know what the thing on the left-hand side of that pipe is part of. What is the input? What is the thing that is a ratio of two numbers? If I had put the United States equals P over Q for some P, Q, and Z, that wouldn't have made any sense. We needed to know that X was a number, not that it was a country. Just another mathematical example to help drive this home. Let's think about the set of all even numbers. Maybe we'll call it E for now. Even numbers are integers that are multiples of 2, right? So 0, 2, 4, 6, 8, minus 2, minus 4, minus 6, minus 8. Those are all even numbers. So how would we write out the even numbers? Well, they're all integers, right? So in set builder notation, maybe E equals the set of all X in Z. That implicitly says the set of all things X that are elements of the set of integers. So what happens on the left-hand side is you get a sense about what you're talking about, such that x over 2, x divided by 2, is also an integer, right? So for the even numbers, 2 divided by 2 is 1. Well, 1 is an integer. 4 divided by 2, well, that's 2. That's an integer. Minus 6 divided by 2 is minus 3, and that's an integer. So the even numbers are the numbers that if you divide them by 2, you get another integer. The odd numbers aren't in this set, right? So the number 1 divided by 2 is 1/2. That's not an integer. So we can write 2 is an element of E, right? And 1 is not an element of E. Now, much like with statements, sets aren't very interesting just in their own right. It's interesting to know how do we combine sets in a way that allows us to make new sets. So how do we combine two sets and make another set out of them? Well, much like with logical operators, we're going to use set operators, and they're just going to allow us to take two sets and spit out another set. The main set operations that I'm going to show you are related to and, or, and not, the logical operations that we had before. And that makes sense because we just talked about how inclusion, an element of, is an element of, creates a statement that is based upon a set, right? And we also know that sets can be used to find all the things for which a given statement is true. That's what set builder notation does. Is it says I'm going to define the set of all things for which a given statement is true, like X is a democracy, X is an even number, or whatever the case may be. And so consequently, of course, we're going to combine sets in ways that are related to how we combine statements, right? I mean, it's kind of obvious when you think about it long enough. Maybe it was obvious already. So much like with truth tables, the main conceptual device that I'm going to use to help illustrate what these set operators are, they're called Venn diagrams. You've probably seen them a million times. So in a Venn diagram, the first thing that we do is we draw the universe of discourse, right? And we're just going to call that capital X for now. And we're going to assume that everything that we care about is an element of X, all right? X is in the background. X is just sort of what we're talking about. It's our context. All right, so I'm going to define two sets that live in X. So maybe here's A and here's B. All right? And so these are two different sets, and I need to be able to turn them into a third set. I want to find a third set that's based on these two sets. And the first one is AND, which we talk about the intersection of two sets, which is just this lens that lives in between the two sets. And this lens is the intersection. And if I write out A intersect B, look, it's even just a rounded version of that wedge, right? A intersect B, well, I can write that out. It's the set of all X in X. It's the set of all things that live in our universe of discourse, such that X is an element of A is true, and X is an element of B is true. So the intersection is precisely AND. This is a good chance for us to introduce a very special set that will come up pretty often. So suppose that instead of the example that we have where there's overlap, suppose that A and B didn't overlap. Right? So A and B don't touch one another. There is nothing for which A is in X is, there are no X's such that X is in A and X is in B. So in other words, this intersection has nothing in it. It's just a set with no elements in it. It's an empty box. Well, that's a very special set, and we actually have a name for that set. It's called the empty set, and we represent it with this Scandinavian letter. That's our symbol for the empty set. And all that means is the set with nothing in it. Now, anytime we have two sets that have an empty intersection, A intersect B equals the empty set, we refer to these two things as disjoint or mutually exclusive, right? So if you're in A, then you know you're not in B. And if you're in B, then you know you're not in A. So precisely speaking, two sets are mutually exclusive if their intersection is empty. Great. Well, so that was our AND. It's logical then to wonder, hey, what's an OR look like in this case? Well, okay. Well, let me just recombine these two. And the OR is just anything that's in at least one of the two sets, right? So I can write A union is the name of this operator, B. And look, it's just a rounded V. A union B. And that's the set of all x's and x. The set of all things that we're talking about, such that x is in A or x is in B. Or both. Notice that the lens, that lens that has both of them in it, that is part of the union as well. So that's our visual representation of the inclusiveness of our OR operator. So we have and, we have or, we need not. Okay, well, not is only going to talk about one set, so let me get rid of set B. So now we just have A. Well, the complement of A, which I'm going to write A little c, or sometimes A overline, that's the complement of A, and that's just the set of all things that live in X, the set of all little x's in big X, such that X isn't in A. Okay? So and goes to intersection, or goes to union, not goes to complement. And we have new ways to make new sets, basically just using the same logical tools that we had before. Well, then you might be saying to yourself, well, we talked about 5 things. Does if-then have some set sort of representation? And the answer is yes. So let's again draw a Venn diagram. And in this case, I'm going to have set A, and I'm going to draw set B, and it's going to be completely contained within set A. Okay? So this state of affairs means that B is a subset of A. Okay? So in other words, B, everything that lives in B also lives in A. So if I wanted to, I would write something like B is a subset or equal to A if and only if. Right? This is like a definition sort of thing. I'll use this set of symbols if and only if X lives in B implies X lives in A. So if we imagine set B being the set of all things such that property B is true, and we imagine set A being the set of all things such that property A is true, then we're saying that property B is a sufficient condition for property A, and property A is a necessary condition for property B. So for example, suppose that set A was the set of all, suppose that X was the set of all countries, suppose that A was the set of all democracies, and suppose that B was the set of all presidential democracies. Well, if a country is a presidential democracy, then it's a democracy. And notice that the subset operator, B subset or equal to A, kind of looks like a rounded less than or equal to sign, right? And essentially serves the same purpose. It says what's a smaller set, where smaller means one set is smaller than another if everything that lives in the first set also lives in the second. Now, what if they're the same exact set? Right? So what if B was actually the same exact, everything that A covered, B covered too? Well, then we would say B equals A, and that means that A is a subset of B and B is a subset of A, and that relates to if and only if. So in other words, set intersections go to logical and. Set unions go to logical or. Set complements go to logical not. Subsets go to material conditional. And set equality, which is to say A is a subset of B and B is a subset of A, goes to if and only if. So now we have a nice clean relationship between the set theoretic world and the logic world. So one thing that's interesting about sets is that all that is needed for a set to be well defined is that the elements are all obviously distinct from one another, right? So if we have the set of all students in this class, I can tell one student from another. I can validate that one student is one student and another student is another student. The order that we put the elements of a set in, that doesn't matter. And if you include a given element multiple times, that doesn't change the set. But oftentimes we care about the order of information as it comes in. So for example, consider latitude and longitude. So you can identify every point on this sphere that we live on called Earth. You can identify every point on this sphere with two numbers, the latitude and the longitude, where one of these is the east-westiness and one of them is the north-southiness. So those two numbers are enough to say where anything on the globe is. Let's think about where Urbana is. Urbana, Illinois is at 40 north, 88 west. That's its latitude and longitude. Okay? So, in other words, I can write the latitude and longitude as a pair of numbers 40, 88. 40, 88 is not the same as 88, 40 in terms of latitude and longitude. And if you just think about sort of any of the algebra that you did in high school, right? You looked at a two-dimensional plane where there was an x-axis and a y-axis. And, you know, sort of 1 minus 1 isn't the same as minus 1, 1. Right? The order matters. Well, when you think about this broadly then, if we think about the set of all ordered pairs of two sets, that's a really important way to link two sets to make another set. So I can take, for example, one real line and another real line, and I represent these real lines with this fancy blackboard R. And if I think about the set of all pairs of numbers where each is a real number, then I can turn this line into a plane. Essentially, I take one dimension and I add a second dimension, the same way that latitude and longitude work. And I say, well, the order matters. An ordered pair is a set of numbers where the order matters, unlike a set. And then you might say to yourself, well, what's the set of all ordered pairs that live in these two sets? And that's called the Cartesian product. Okay? So whenever I use this times symbol between two sets, that means take the Cartesian product. And how is that defined? Well, let's say A times B. That's a new set. The Cartesian product of set A and set B is a new set. And it's a set of all ordered pairs, little a, little b, such that A lives in A and B lives in B. So that's the Cartesian product, or sometimes just the product of two sets. And it's just a way of saying I can take an element of one set and an element of another set and combine them in an informationally meaningful way. I can take one real line, another real line, and use it to identify every point of a plane. I can use latitude and longitude to identify every point on the sphere of Earth, right? So this Cartesian product is a fourth way to make a new set out of other sets. And it's going to be a really important tool for us because we're oftentimes going to care about a combination of things where we know where everything lives, we know the constituent sets that everything is part of, but we want to think about them all together at once. You'll see plenty of examples moving forward. So for example, we mentioned that there are 4 suits on a deck of cards, right? So there's spades, clubs, hearts, and diamonds. Every card also gets a denomination. These are aces. You can go ace, 2, 3, 4, up to 10, jack, queen, king. So I've got 4 suits, S equals hearts, diamonds, clubs, spades, and 13 denominations, D equals A, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. The Cartesian product of those two sets is just every pair. Ace of hearts, 2 of hearts, 3 of hearts, ... king of hearts. Ace of spades, 2 of spades, 3 of spades, ... And the same for all the suits. So the Cartesian product is just the way of saying, take all the possible denominations and all the possible suits and combine them to get all possible cards. Now I promised you that once we talked a little bit about sets, then we would be able to introduce 2 more logical operators. And to do so, I want to talk about a special kind of set that we use pretty often. It's called an indexing set. So oftentimes, I'll want to talk about I want to talk about the set of all countries, and I want to know something about the set of all countries. Let's say that X sub I was the gross domestic product of country I, where I was an element of the set of all countries. Armenia, ... Zimbabwe. Okay? So X sub I is country I's GDP. So I have X sub Armenia, X sub Zimbabwe, X sub every country, right? So I have all of those. So this set of all countries in this example is my indexing set. And I might even assign every country a number. Maybe Armenia is country 1 and Zimbabwe is country 200. Great. So once I have an indexing set, I can even think about a set of statements, right? So let's say that I wanted to know whether a given or every country's GDP was above a certain threshold. So which countries have a $5 trillion GDP? So I have a bunch of trues and falses based on whether that country's GDP is over $5 trillion. Well, how would I combine that bunch of statements, one for every country? Okay. Well, I might want to say for all countries, for all I in N, for all countries, PI is true. Right? So this upside down A operator means for all I, where I is just a stand-in, I is a little pronoun for Armenia, Azerbaijan, Austria, Australia, Angola. I'm running out of countries that start with A that I know the name of. Argentina. I have a PhD in this. Right? So for all those countries, we have a bunch of statements, and we want to make the claim for every one of them, PI is true, right? In other words, you can think about this as if it's like a gigantic and, right? So like P1 and P2 and P3 and ... and Pn minus 1 and Pn, where like little n is how many there are. Right? So when I say for all I and n, Pi is true, essentially what I'm saying is P1 is true and P2 is true and P3 is true, ... That's called the universal quantifier. And it's our way of saying that once you've defined a set of statements, now we can combine multiple statements, not just two statements. Right? So before our and operator only combined two statements. We had the United States is a democracy, Canada is a democracy, and then the new statement, the United States and Canada are both democracies. For all, just basically iterates that for all elements of a well-defined set, that indexing set. The final thing that I need to show you is sort of the universal quantifier stood on its head. Sometimes you don't want to say for all, you want to say in a given set, there exists at least one, okay? So, for example, there exists some I in N, where I use this upside down E to say there exists. So there exists some I in N such that, oftentimes you'll use the such that, you'll use pipes or a colon there, such that George Washington was president of country I. Is that statement true? Yes, because there does exist a country. Now, suppose that I had made the statement, there exists a country I, such that Robert J. Carroll was the president of country I. Oh, don't vote for me. That statement is false because there doesn't exist such a country. So in other words, when I say for all I and n, Pi is true, or there exists some I and n such that Pi is true, these are statements that are either true or false, because that's what a statement is. Now, if you think about it, the there exists means iterate the or operator, right? So there exists some I and n such that George Washington was president of country I. That means Pi is true for at least one I in n, right? So it's like P1 or P2 or P3 or ... or Pn. So the existential quantifier is just a way of concatenating or a bunch of times. So those are our big 7. We've just encoded 7 everyday parts of plain language in a precise way. And, or, not, if then, if and only if, for all and there exists. Those 7 tools are a lot that you don't realize just how much we're going to be able to do with just those 7 tools. I want to show you something important that relates to how all of this works in terms of the universal and existential quantifiers, and in particular how you negate a statement that includes one of these. So if I said to you, let n be the students, all the students in this class. Suppose I said to you, for all I in n, so for all students I that live in the set of all students in this class n, pi is true, where pi means that student I was born in the state of Illinois. So for every one of you, there's like 50 in the class right now, so n has 50 people in it, and I have a bunch of statements. Pi is a statement for every one of you that's true if you were born in the state of Illinois and false otherwise. Okay? So if I wanted to say that that statement was true, I would need it to be the case that every one of you was born in the state of Illinois. For that to be false, if I wanted to render this false, if I wanted to negate this statement, I wouldn't say the following. I would not say, for all students I in n, student I was not born in Illinois. That isn't the proper negation. I don't have to change all of you to non-Illinoisians in order for the initial statement to be wrong. What I need to do is say, there exists some student j in n such that pj is false. So if I say to you, every student in this class was born in Illinois, for you to refute me, you don't need to show me that every student wasn't born in Illinois. You just need to show me that one student wasn't born in Illinois, which I'm assuming is the case in this class. I wasn't born in Illinois either, so hi. Right? So to negate a for all statement, you use a there exists statement. And you're like, does that work in both directions? Yes. So suppose that I said to you, there exists a student I in n. Suppose I said to you, one of our students, there exists some student I in n, such that pi is true, where pi is true when student I was not born on Earth. You would say, no, you're wrong, and the reason I know that you're wrong is that every student in this class was born on Earth. So in other words, for all students I in n, pi is false. So to negate a there exists, we use a for all. To negate a for all, we use a there exists. So just to review, in the world of sets, a set is a well-defined collection of objects. We can combine sets through things like intersections, unions, complements, and Cartesian products. Also, if we have an indexing set to talk about a bunch of different sets, then we can also concatenate those, so we can have a big union, which is sort of, if I have a collection of sets, A1, A2, A3, ... AN, if I have a collection of sets where every one of these things is a set, I can combine them all with this big union operator, and that's just A1 union A2 union A3 ... union AN. I can also do a big intersection of them, and that's just the smallest set that lives inside all of the other sets. So even though it's really fun to talk about sets, I think it's fun anyway. It's fun to think about how you can organize all of the different items. And if you're interested in like what a database is, you have to think a little bit about what sets are. So it's fun to think about sets, but eventually we need to think about how we can relate sets to one another, not just combine sets to form new sets, but make arguments about how certain kinds of sets relate to one another. And it turns out that's exactly what a function is. So now let's talk about functions. So when we start to talk about functions, we're gonna characterize sets a particular way. So for all of the formalism that we just introduced about sets, oftentimes you can think about a set, and this is a useful way to proceed, as just a blob with some dots in it. So here's set A, it's a blob with dots, where every dot is an element of A. And let's come up with another set, B, and it's just a blob with dots in it. Just to preview the example we'll be talking about in excruciating detail next week, suppose that A is the set of alternatives. So I go and I open my fridge, and there's a bunch of different kinds of beverages. Okay, so maybe A is the set of all beverages that were in my fridge. And so I have a Diet A&W. I have a LaCroix, key lime, thank you very much. I have a bubbly blackberry. And I've got a La Colombe. I feel like an idiot. I mean, I am an idiot. Triple shot draft latte. This stuff is the only reason that I'm able to speak semi-coherently this morning. None of this is an advertisement. So A has 4 elements in it. Diet A&W, this thing, bubbly, and LaCroix. So maybe B is the real line. The positive numbers, we'll say maybe R plus. And you might be saying to yourself, well, what do I care about the set of all numbers? Why is B the set of all numbers? Well, there's a couple of different functions that can turn a can into a number. And you're like, what is he talking about? Okay, what about calories? So consider the rule that says, take a member of A, which is a can of something, and spit out a number that tells you how many calories are in that can. The LaCroix goes to 0. The bubbly goes to 0. The Diet A&W goes to 0. All of these are 0 calories. And you're like, by the looks of all the 0 calorie stuff, you should not look like this, round man. I know. And this one, 100 calories. So I've got a way of saying, well, take the A&W dot, send it to 0. Take the LaCroix dot, send it to 0. Take the bubbly water, send it to 0. And take the La Colombe and send it to 100. So that's a function, right? There's a calorie function that reads in a can and spits out the number of calories in it. There's also a price function, right? So probably a Diet A&W, if I bought this can at a mini mart, this is probably $1. These are a little bit fancier seeming, right? So these are probably like $1.50 at a mini mart, right? And of course, these things where they know they're going to get yuppie idiots like me to buy it, like this is probably $3 or $4 or $5. So again, there's a function. There's a price function that reads in a can and spits out how much it cost. So what a function is something that reads in one item, one element of a set, and spits out an element of another set. Right? So when you learned functions in high school, it was probably something like f of x equals x squared minus 9x plus 2. Right? Well, what did that mean? F of x equals x squared minus 9x plus 2. Well, that means take a number x and do this cookbook recipe on it. Here's an algorithm for what to do. So take the number. Let's say that I took 1. Let's say that x equals 1. So this is a rule that says take the 1, square it, now I've got 1. Multiply it by 9 and then subtract that from what you had. So I've got 1 minus 9, that's minus 8. And then add 2, minus 6. F of 1 equals minus 6. That's just a rule. It just so happens that in this case, A, the input set, is the real numbers, and B, the output set, that's the real numbers too. So most of the functions that you got taught were just ways to map real numbers to real numbers, or maybe natural numbers to natural numbers, or something like that, you know? But in this class, we're going to need to be thinking about functions a little bit more generally. All that a function is a well-specified rule for taking each dot in the left set to one and only one dot in the right set. That's what makes a function a function. Every dot in the first set gets sent somewhere, and it only gets sent to one place. In terms of terminology, whenever I introduce a function, I'll write it something like f maps A to B. Whenever you see this, f colon A arrow B, that means f is a function, and it reads in things from A, and it spits out things from B. That's all that a function is something that reads in one thing and spits out another. So just to give you an example from what we'll be talking about next week, we'll have an alternative set like this, and we'll be wondering, hey, is it possible to have a function that reads in alternatives and spits out how happy you are from consuming that or from that being the outcome, right? So if I have to choose something, how do I choose it? Well, the usual myth goes that every one of these beverages is associated with a utility number in my brain. And in that utility number in the brain tells me what to pick. Now, none of that is true. We'll talk about that next week. But it means that this utility function, that's a device. It's a set of arrows that reads in alternatives and spits out happiness numbers. So there's some special kinds of functions. So if every member of the domain, the first set, gets sent to its own special element of the second set, the codomain, right? So whenever I write f a to b, a is the domain of f, and b is the codomain of f. So if every element of a, the domain, gets sent to its own special element of b, the codomain, then we say that function is one-to-one. So what that means is that distinct inputs yield distinct outputs. Any two inputs that yield the same output must be the same input. These one-to-one functions are very useful. And if it's true that every element of B, the codomain, gets hit by at least one A, then we say this function is onto. And the set of all B's that get hit is a term that you probably are more familiar with. That's called the range. And so functions, we can talk about different kinds of functions, and we will throughout the class. But really, I just want you to think about functions as rules that make arrows that link dots within blobs. And for this, you're paying. You're gonna see very quickly that this framework for understanding things in terms of sets and then relating sets to one another substantively, right? So the utility that you get from drinking this is not the same as the utility that I get from drinking this. And so our arrows that read in coffee and spit out happiness numbers, our utility functions will be different. That isn't a mathematical point. That's a mathematical crystallization of the fact that you and I have different taste. That's an encoding of the fact that you and I have heterogeneous preferences. That's a big deal. And the fact that we can figure out what it looks like in terms of stupid blobs, stupid dots, and stupid arrows is a really big deal. It means that we've encoded not just the world, but ourselves. Whoa! Let me put all these drinks back before they get warm and I get in trouble. So, what did we talk about today? Well, we didn't talk about IR very much. But we talked about how to talk about IR. Even if you don't believe in rationalism, which I don't know what that means, but even if you're not going to wind up being a rationalist, thinking precisely and thoroughly is important. And you shouldn't be dissuaded by the mathematical aspects that we've just been discussing, just because it just so happens that sociologically they've been linked with rationalist international relations. We talked about logic a little bit, just a tiny, tiny bit. You can take a whole class, you can take a sequence of classes in logic. You can get a PhD in philosophy with a focus in logic, right? Logicians are still inventing new important methods, right? This isn't over. This started with, I don't know if it started with the Greeks, but at least it goes back to the ancient Greeks, right? Isn't that amazing when you think about it? Likewise with politics, for the record. So even just elementary logic, just thinking in terms of precise statements that utilize firm definitions, that's a very big deal. And so the fact that we could take statements and make them about the real world, and then combine statements using 7 operators, and, or, not, if then, if and only if, for all and there exists, those 7 operators on logical statements give us not just a way to take a bunch of statements and combine them, but also to form chains of reasoning that allow us to follow from assumptions to conclusions, essentially axioms to hypotheses. It's really amazing that we're able to do that through just some very simple, straightforward tools. Likewise with sets. So using roster, set builder, or even just straight linguistic notation, it's very easy for us to write down the sets of all objects that are linked via some property, right? So we can write down very easily the set of all countries, the set of all individuals. If I said to you the set of all registered voters in the United States, I just identified hundreds of millions of people without having to check the census website, right? You know, it kind of stinks that I don't have all the data that I might want about that. Actually, it doesn't stink from a privacy standpoint, but you know, you might be somewhat unconvinced and this is super powerful, but just being able to play with the concept of a registered voter in such a clean way so easily is a very big deal. And once you get used to thinking that way, it's going to be, you'll see that this is actually a personal innovation that you'll experience. So we talked about sets, which are a great way for us to keep our thoughts organized. They're a great way for us to collect different kinds of actors, different kinds of alternatives that they have, different kinds of choices that they face, different kinds of outcomes. Sets allow us to capture all sorts of seemingly different but also conceptually related objects, the elements of those sets. And we talked about how we can combine sets in important ways. Some of those were based on the logical operators, so unions are kind of the same as or, intersections are kind of the same as and, complements are kind of the same as not, subsets are kind of the same as implication, and equal sets are kind of the same as if and only if. We talked about indexing sets, which we're going to use again and again. We're not going to talk about them, we're going to use them so often. And these are powerful tools that allow us to say that something is true for all, or that there exists some entity for which something is true. And then we introduced the notion of a function, which isn't just a way to turn one number into another number, like you learned probably in high school algebra. It's so much more. It's a way to get from one set to another. It's a way to link two sets, whether it's numbers to numbers, cans of Coke to happiness numbers or prices or calories. There's all sorts of different ways to link sets. We'll be doing it again and again in this class. So actually an interesting exercise is whenever you get a little bit confused in the topics that we'll be discussing, just say, what's the sets, functions, and logic foundation of what we're talking about? What are the definitions in question? What is a statement? What makes something true or false in this world that we're constructing? And once we've done that, then we're going to be able to take this gigantic reality that we find ourselves in, which is way too complicated for us to ever try to keep track of. We're going to use it to inform a little mathematical fable world called a model. And that model is going to involve sets and functions and logic and definitions. So we're going to take this big, chaotic, confusing, embarrassingly complicated world that we could never hope to keep track of. We're going to convert it into a fake mathematical world, a fable, a simplified reality that we can learn something from. We're going to operate on that set, function, logic, definition, fake world that we create. And then we're going to use what we learn in that fake world to go back to reality and say, hey, does this help me learn something? Have I gained new insight? Do I now know something I didn't know before? Does a new concept seem super important to me where once it didn't? What have I learned from the exercise? And that's what hopefully you get out of this class is you'll learn some of the things. So I want to conclude with two related provocative thoughts. One, mathematics is hard to define in its own right. What makes math? One common definition of mathematics that even though we've been doing mathematics for millennia, this definition is relatively new. It came from the 1980s. So did I. Mathematics is the science of patterns. Sort of number theory and algebra are the science of patterns of counting. Geometry is the science of patterns of shape. Calculus is the science of patterns of little flow. Topology is the science of patterns of closeness. Game theory is an applied branch of mathematics, which means that it's the science of patterns of something. And it's the science of patterns of strategic interdependence. And strategic international relations, therefore, is the science of patterns of strategic interdependence on the international scale. Why do we engage in the science of patterns then? And the answer is to make previously invisible things visible. When an aeronautical engineer uses differential equation models, I'm assuming, I don't know, I flunked out of engineering school. When they do that, they're modeling air patterns, drag, whatever. And in so doing, they make it perfectly visible in the context of their model that a gigantic, metallic, heavy, dense airplane moving at a certain speed with its wings set a certain way will fly. That makes something incredibly powerful, but that had been invisible, visible. So what's the analog for international relations? What are things that are invisible that we would like to make visible through this process of encoding working on the fake world that we encoded and then going back to reality. And I want you to think about that, because I don't have a firm answer right now, but think about all of the different incentives, all the different patterns of interaction, all the different unknown patterns of strategic interdependence that happen in international relations. These patterns are invisible to us until we come up with an appropriate mathematical representation that allows us to identify them. Even though our brains are predisposed to identify patterns, one, they don't identify every pattern that's there, and two, sometimes they identify patterns that aren't there, right? They overfit, or we use stereotype bias or something like that. That's our goal, is to make invisible things visible by identifying patterns of strategic interdependence through the science of strategic interdependence, which is mathematical game theory. Other than that, this is a simple topic. Provocative thought 1. Provocative thought 2. Is mathematics discovered or invented? Whoa. That's a heck of a question. Well, in a sense, it's invented, right? There's a famous quote attributable to mathematician Leopold Kronecker. He said that God invented the integers, and all else is the work of man. And the idea there is that, the counting numbers, the process of counting is sort of baked into humanity. And Kronecker was a religious person, so he thought that whatever was baked into humanity was also baked into a man's relationship with God, something metaphysical. And so, yeah, the real numbers, negative numbers, 0, these are concepts that we've invented over the years to try to help us to understand what's going on. When we impose these new features into this gigantic mathematical machine, sometimes they have unintended consequences or unexpected consequences. And oftentimes there's a process of discovery that allows us to figure out what other things are true as a consequence of our new developments, like 0 or negative numbers or real numbers or whatever the case may be. So there's this unexpected, there's a generative process. So we make inventive decisions to try to say, well, I think there's a concept of nothingness, and so I need a 0. Well, once 0 is included in your set of numbers, now there's unintended consequences. Something new gets generated unintendedly. And so actually, the process of mathematics is neither one of pure discovery nor one of pure invention. It's one of design. Part of our job as strategic international relations students together is to design a branch of applied mathematics that we think works especially well for international relations. Now, the features that ought to be in that designed branch of mathematics that we're talking about, that is both inventive and discovery-laden, that design process, what features ought to be in the models that we write down, is a substantive question. There isn't a mathematical answer to whether countries have different preferences from one another or not, or whether preferences matter or not. So math can't tell you whether the realists or the liberals are right. But if you ask me, the process of arguing about what ought to go into the models is the most fruitful argument that we can have. And so as you encounter more international relations scholarship, be it formal or informal, mathematical or not mathematical, rationalist or not, whatever the case may be, whatever controversies or tensions you identify in the scholarship that you read, think about what that fight would look like if it was about what deserves to be in our designed branch of mathematics called strategic international relations. Thanks for listening. I've talked myself hoarse, and you probably have a massive headache from listening to this thing that I'm throwing at you. I hope you've had a good time. This is step 1 of 15 for us, and I'm really looking forward to seeing what we can learn together. I'll see you on Monday for the first meeting of the class.